Okay, so we are back with class 16, and this is video 3, and here's an additional example. I believe this is an example that's inside of Munson, and we're going to use some data this time. So a relationship between the pressure drop per unit length along a smooth-walled horizontal pipe and the variables that affect the pressure drop it's to be determined experimentally. In the laboratory, the pressure drop was measured with a 5-foot length of smooth-walled pipe having an inside diameter of 0.496 inches. The fluid is water at 60 degrees Fahrenheit, and there's the viscosity and the density. And the tests were run, and velocity was varied, and the corresponding pressure drop was measured, and here are the results. So we want to use this data to obtain a general relationship between the pressure drop per unit volume. Okay, so what we would do as part of this, if this wasn't an already established, very well established problem, would be to take that pressure drop per length as the main variable that we would have, and we'd find what the other variables it depends on. Well, it's dependent on the diameter, it's dependent on the density and the viscosity, and we could tell that because they gave them to us, but also just from similar problems that we know are true, this must be true, and the velocity. So these are what the things are dependent on. And if we do the Buckingham pi on this, we find that we have our dimensionless groups are the diameter times that pressure loss divided by the viscosity and the velocity squared right in there. Okay. And remember, this is delta P per L. But you can kind of tell that this is close to being the Euler number, by the way. And also closely related to the Bernoulli's equation as a ratio. And you can see, because you have like pressure per length, but then times the diameter. So that's like a pressure on top, and here's the dynamic pressure on the bottom. So as that's going to be the dependent, or one of the dimensionless groups that we're going to use here, that ends up being Reynolds number, right? So we could plot these out. So let's plot out this data. So this is velocity versus pressure drop, and we should always use, when we're dealing with data, use this scatter plot right there. Don't use the one that connects lines, because data is random, so you're going to have zigzag lines all in place. And then just to keep track of this, we're going to say that this is raw data. Let's see, I'm going to do certain things that I think are prudent because I'm going to put this into a Word document. I'm going to get rid of that border. I think it's silly to have that border there. Technically, when you have when you're going to do like a report, you should put the figure caption underneath. So I don't like the fact that Excel does this and puts this title on the top. I see a lot of people in reports, they have this thing on the top. It's unnecessary to name the thing, because you'll usually will have a figure caption in there. But just to keep this in Excel, we'll leave it like that. We also want to add in the primary and the secondary, sorry, not the primary and secondary, but the primary horizontal and the primary vertical, and label these. So this is going to be the velocity, and that's the symbol for it. And this is going to be what was this measured in, by the way? What did that say? It was feet per second. I always put them in brackets. This is just good practice. Over here, we'll go pressure drop per length, and I guess I don't really. I could put in there all the information, but I'm going to be lazy, and I'm going to say pounds per. It's really cubic foot, right? Let's see if it'll let me. No. So I think it's just good practice to make that look like a cube. Let's see. Highlight it and go to font and go to superscript. Make it look good. All right. So this, like, maybe we would change the dimension of it. So I'm going to add a trend line, and that's the reason why we only use the data points, right? When doing an analysis here. Well, I mean, when doing a presentation, because these data points could be all over the place. So we want to draw a line that represents this. In this case, it looks like it's going to be like a polynomial right here. Second order polynomial works pretty well. Third order polynomial, it actually might be a better. We could find that out by making sure that we put the equation in there. And we say, actually, that works out just well. That's interesting right there. That's right to the third right there, and we have an R of 1. By the way, when we're dealing with that equation, I'm going to change this over here and change it to scientific, just so we have enough decimal places or sig figs, and so we're changing it to 3 sig figs with scientific. We'll make, 3 decimal places with scientific will ensure that we always have 4 sig figs. So that's a pretty good curve fit, and probably that's how they generated this, was to change this thing along like there. But now we have we want to manipulate this data, right? So here's the raw data from the experiment, but let's use the dimensionless groups here, and so we go I don't know, press. I don't know what did I call this depressionless group right here? I'll go pi1. I'm lazy. And we'll call this one pi2. Oh, sorry, pi2. Pi2. Which we actually, maybe this is actually the Reynolds number is what we're going to make right here. And so we'll put it up here. So I'll go equals, and I'll have the diameter, which already turned into feet. They gave it to us in inches. See, like right up here, you can see that divided by there. So turn it into, just get the dimensions the correct way. And so get that diameter and hit F4 to give the dollar signs to it, and multiply it by the pressure drop right there, which should be pounds per square foot. But that's pounds per square foot per length. So divide by the length, 5 feet. And we need to always use that cell, so hit the F4, put the dollar signs in there. And divide that by the density, which we will always be using that same cell. So, and again, the dollar signs. And then lastly, divided by the viscosity, and we should hit F4, boom. And we have that value right there. And I kind of want to see that as a number. See, I think I might have made a mistake here. So let's double check my work. Right, I took I should have made the velocity squared. What did I do wrong here? No, I said that, yep, I made a mistake. It is not the viscosity. It should have been the velocity. Boom, him. And he doesn't need the F4 because it's going to vary time, and we're going to square it. Oh. So what happened here? Made another mistake somewhere. A9v squared. We'll check. Diameter times the pressure drop divided by the length divided by the density and divided by the velocity squared. Okay, no, maybe that's fine. Okay, yeah, actually, maybe that's fine. That is fine. Okay, sorry. I was thinking of the Reynolds number. Yeah, okay. So come back over here. That was the correct. And then go, now we go to the density, but that's going to be F4, times the velocity, times the diameter, F4, and then divided by the viscosity, right, F4. And that's the one. Okay, so that was what I was expecting in terms of the number. So I'll go to the number here, and we see that's like 4,000 right there. And I'll center these, and now I can hit this, double click on that little corner thing, and it'll drop it down. So let's reuse this graph. And now instead here for the data, See, it's not letting me grab the data. Why aren't you letting me grab the data? There you go. I can go ahead and move that over and move this over. And now you can see that the graph ain't so great right there, right? We're graphing this, and that doesn't really, and now this is, I'll go to this dimensionless groups, and now this is the pressure drop pi term, and this is Reynolds number, and they don't have dimensions, so we don't have to put the dimensions into the brackets. I went Reynolds number, come on. Reynolds number. Oh, actually I have this backwards. Sorry, so I have to change this around. Let me grab this, and I need to swap them out. So let's swap that, boom. Okay, so there you go. There is Reynolds number. Reynolds number should be a big number, right? A large number right here. And so right now, let me fix some of my numbering here. I guess it doesn't quite matter just yet, but if we were going to fix this and use this, we would want to have, we only need 3 decimal places right there, right? So 0.25, yeah, right there. We only need 3 decimal places because we have that 5 right in there. And then here, actually, this looks actually pretty good. So we're looking pretty good. This is a terrible thing here. So let's try a couple. So linear, nope. Exponential, nope. Logarithmic, ooh, that actually looks pretty good. Let's, yeah, here you go. So here's the equation that's describing that. So we get 0.9905 r squared term. Let's see if we can improve that. Let's see, we'll go down to this guy right there, back to him, and up to there. Yeah, okay. Polynomial, we already saw. We could like change these polynomials right there to higher degrees and get it to go up, but that curve doesn't look like it makes a whole lot of sense, right? So let's go back up to here and go to power, and all of a sudden we get a nice term. Like look at how nice that is. That's good. It's like 0.996 for this. And can we zoom in to see that any better? Let's see. We could see that the value is like, okay, so it's to the negative 1, e to the minus 1. So this is like 0.1503, and this power is like 0.2456. That's actually, we will discover that's actually really close to what we expect from a classic experiment done by Blasius. I don't know what Blasius' first name is. I should learn his first name. It'd be nice just not to call people by their last names. And then maybe we also want to see this, because oops, didn't mean to do that. Meant to move to another place and copy this over so that we could see it. And now let's change this to a log graph. So we move this over, and axis options, there you go. Make it log, and then make this one log. And as is true with a power type of arrangement, it's the same equation right here. You can see it's a straight line, and that's actually a means by which to come up with this curve fit yourself for a power, is that it's going to be a slope and let me see if I'm saying this right, a slope and an intercept, if you will. But anyway, you could find a coefficient and an exponent. To be able to see this better, we want to change the range, maybe make it 0.1. Makes it a little, no. Oh, I see. Oh, wait, I'm doing the wrong way. Oh, no, I'm sorry. That's the Reynolds number. Let's see. We want to go to 1,000 as the minimum. There you go. There you go. We stretch it out, and because Excel has like limitations, it won't. I haven't figured out a way, at least, to be able to get the numbers to show up right in here. You could make like, you know, go 3,000 if you wanted to. 3,000 right there. So, but now it goes to 3,000 to 30,000. So I think keeping it on the tens is better. And I also like when it's to usually use the scientific notation, and it doesn't need any trailing zeros here. In fact, it doesn't actually need this trailing zero right there. So we can get that right there for the log scale up for the Reynolds number. And then do this thing the same thing. We don't need to have, we want to maximize what we can see right there. And so here is where I would go 0.1 instead for this. Whoop, I do that wrong. Yeah, let me reset. So the maximum is 0.1. There you go. At least you get the maximum out of it, and this is sort of because of the limitations of Excel, as I mentioned. But you know, we have that same equation right up above. So what we've learned here is that we have, you know, the pi terms have a relationship in it when it's a power type of scenario here that look like this right there. And so what Blasius, and so the A that Blasius came up with was 0.15, and the N was approximately negative 0.25, right? From the awful log paper, so the Blasius equation, which came out in 1911, what he established was for very smooth pipes, we had the relationship for the pressure drop per length times the diameter, and density squared is going to be equal to 0.1582. That's what he found. That's what Blasius' results were, where you take the Reynolds number, and maybe it was just right Reynolds number. I guess I already started. Reynolds number based on there, but based on diameter, not length, as we would often see, raised to the negative 0.25. This was Blasius' equation. And we see that from this data. Now, I have a strong suspicion this data was kind of fudged, because you could see from here that it's a perfectly cubic curve match. There's no way that actually happens in real life. If you were to take a test yourself, you would have points that didn't make any sense. They'd zigzag all over the frickin' place. That's why you don't use you don't use these right here for that. You use the data. When it is data, you use the data points and then you add it. And you don't if you base a curve on an equation that you're plotting out, you don't use the data points, right? You would then use this right here, this kind of curve right there. Just want to make that clear. So anyway, I think that's all we had for this equation. But this is an informative problem, because you can see now how we could go from experimental data to an equation, an empirically obtained equation that will now serve to be able to when to calculate for a new scenario. But you have to remember that this thing is limited to a Reynolds number that falls between 4,000 and 98,000, right? So if you have something that's 150,000 Reynolds number, you should not use this equation, because you'd be extrapolating, and you can interpolate, but you can't extrapolate, and that's either upwards or downwards, because if it's something is less than 4,000, you wouldn't want to use that equation. So there you go, the end. Too long of a video, but I described a lot of things, Excel things.